It is a great pleasure to give you a report on our recent work entitled A Shared Aperture Antenna with High Aperture Reuse Efficiency and High Isolation based on the Quasi-Yagi Structure. Sensing and communication as the two major functions of the information system, the integrated design of the two is one of the development trends of information technology and intelligence, which also generates the urgent demand for sensing and communication shared aperture antenna. Facing the design difficulties of small size, high integration and low coupling, integrating well-designed filtering antennas by stacking is an effective method. The proposed shared aperture antenna covers two frequency bands by incorporating a folded dipole antenna for the lower band and a dual polarized planar bowtie antenna for the higher band. The lower band element is positioned beneath the higher band element. The stacked shared aperture scenario forms a Quasi-Yagi structure in the vertical direction. This work adopts the Quasi-Yagi principle to analyze the shadowing effect of the stacked aperture antennas for the first time. A general guideline is presented for suppressing the shadowing effect, which provides useful insights into the selection of appropriate antenna geometries, spacing, and polarization to achieve directional radiation patterns. Lower band antennas are usually larger in size than higher band antennas. In this work, it is proposed to achieve a small aperture size by reducing the size of lower band antenna, which improves the aperture reuse efficiency considerably. Etched slots and resistive loads are used to adjust the resonance frequency. This work also elucidates that appropriate resistive loads does not exert a significant influence on the realized gain. Since the shared aperture is very compact, mutual coupling between all ports is significant. By introducing low-pass response to the lower band antenna, as well as introducing band-stop response to the higher band antenna, the isolation between the lower band and higher band antenna exceeds 30 dB. Those filtering responses are fully integrated without increasing the antenna size. The proposed antenna was fabricated and measured. The measured results indicate a -10 dB bandwidth from 0.77 to 1.06 GHz for port 1, and a -10 dB bandwidth from 2.2 to 6.6 GHz for port 2. The port isolation is greater than 30 dB across the entire operating frequency. For a brief summary and prospect, a new shared aperture antenna that covers the UHF, S, and C bands with high aperture reuse efficiency and high isolation is proposed. The major innovations of this manuscript include the theoretical analysis of shadowing effect, the improvement of aperture reuse efficiency, and the reduction of mutual coupling. The design concept is expected to be applied to the design of integrated sensing and communication antenna apertures for more frequency bands and shared aperture arrays.